David?
Can you hear me?
Yes?
Good. Yes,
So,
we're ready.
are you ready?
We are.
Okay. So, yeah, you can go.
Okay, thanks a lot, Anna. Um, so, thank you everyone for being here today to listen, and thank you to Paul for the excellent keynote that I just heard, and thank you to Ian and Jason for that thoughtful paper about alternator a second ago. Um, So I have a long list of co-authors, but I'm going to be doing the presenting today for the sake of efficiency. But just quick shout out to some of the co-authors that are here in the room. I believe I saw Nick Brown-Hernandez and Bernard Gray and Deandrew Stewart here in the Zoom room with us. And so the paper, of course, is online. What I'm going to propose to do in today's presentation is to give a fairly quick review of the paper and then focus on some particular issues that I think it's most interesting to discuss with this group. Okay. So first of all, some basics about Estuary. It's a browser-based live coding platform that emphasizes having multiple live coding programming languages interacting in the context often of collaborative networked ensembles. It can be used in a wide variety of both co-located and distributed situations. The flagship server for Estuary at estuary.mcmasterc currently sees about 3,000 connections per month, and the source code is licensed on a GPL3 basis. And over here on the right of my slide, we see a video from YouTube from a Cybernetic Orchestra album that uses Estuary. And I think this kind of sums up a common aesthetic you see with Estuary. The interface is divided into different panels that are being used by different people who are identifying themselves with names. And in some of the panels, you see different programming languages. By the way, you can find lots of cool videos of people using Estuary by just searching online for Estuary live coding, for example, on YouTube. So a few quick points about the philosophy of Estuary, beyond the things I've already said. A primary goal is to facilitate choices of live coding languages, especially within and across groups. And I think one of the things that this facilitation of choices does is it allows us to unsettle all too definitive conceptions of what programming and languages are, like Jacques Derrida's unsettling of what natural language is in the monolingualism of the other, or on a slightly different tack, Wendy He Kyung Chun's unsettling of instrumental ideas of programming in programmed visions. The development of the platform has also been guided by a particular philosophy about safety and security on the web, or we could say trust, fun, privacy, access, all these other related concepts. And that philosophy is to try to have these things without having users, without having identified users, via multiple levels of pre-shared passwords. And this might be related to Wendy He Kyung Chun's critique of a Web 2.0 security that is, in the end, no security at all. So how does it work and how is it built? So there's a client, which is an HTML, CSS, JavaScript application, and it provides widgets for editing code and other interfaces for algorithmic music, such as step sequencers. And the client is responsible for all parsing and rendering of live coding languages in Estuary, which is what enables Estuary to be used in a batteries included, zero installation way. There's a server, and the server provides the client as a bundle of static files, and it has an ongoing WebSocket connection with each client that is basically only for the purpose of collaborative editing of shared code and interfaces. It plays no role in rendering whatsoever. The server also serves some default media files, such as audio samples. And in terms of how the project is built, the source code is mostly the strict functional programming language Haskell, 91.4% according to GitHub. The Glasgow Haskell compiler is used to compile the server. An advantage of this is the really solid abstractions for scalable concurrency that we get. and the reflex platform in GHCJS are used to compile the client from Haskell into JavaScript. And so this allows us to incorporate languages that exist already as Haskell libraries, and it allows us to reuse code with the server. So Estuary's been around for a number of years now, and the paper describes some of the developments over the last 3 or 4 years or so. One of those is a shift from musical to audiovisual live coding in the form of incorporating languages that are strongly oriented to visual results or visual results in close association with sound and music. So there's 3 base languages in Estuary that have been developed over the last few years. Punctual is a Haskell-like language that's built around the idea of programs that are simultaneously translated into web audio and WebGL results. Cinecero is a language to control the playback or projection of fixed video and image files, as well as text and typography within the browser. And Hydra is a popular JavaScript library or dialect for the live coding of video synthesis. And this has been incorporated into Estuary in the form of a restricted abstract syntax tree to guard against the security or halting problems we might have in ensembles if people were entering just any random JavaScript, and we were using the browser's evaluate mechanism to make that go. The slide over here on the right is from a performance of a duo I am a part of called Very Long Cat with Montreal tabla player Sean Matavetsky. You can see Sean here on the right, and the language Punctual is being used here on the left, both to generate synthesized sounds and to generate generative visuals that are related to those sounds at the same time. So another major aspect of Estuary development over the last few years has been a move towards the platform becoming more of a modular sandbox of widgets that do different things that live coding ensembles might be interested in doing. So a lot of work has been done on enabling the on-the-fly addition or renaming of web-located audio resources with similar functionality for images, videos, and other things coming soon. Estuary, since the earliest days, has had a view system that allows multiple simultaneous customizable views of the state of a collaborative ensemble. From those earliest days, there were widgets like a text code editor, a structure editor for the title cycles language, a step sequencer, and labels that people would use to claim space in the interface, for example. But in recent years, we've been paying attention to developing new collaborative widgets, like widgets for live coding turn taking, live coding roulette, visualizers of time, meter, and computational performance, notepads, calendars, multiple chats embedded next to other widgets, etc. So these new widgets are kind of hot off the press, and they're just starting to percolate into the community of practice that is using Estuary. Finally, under the rubric of modular things that have been developed in recent years, we have JSOlangs, which is an Estuary affordance. It's a portmanteau of JavaScript and Esolang, or esoteric programming language. And JSOlangs are little languages that are defined on the fly using JavaScript and that are transpiled to other Estuary-based languages. And the image here on the right is just a selection of some new and old Estuary widgets that can be deployed in different ways. So the paper goes into much more detail about further applications, but I just wanted to briefly mention that the paper does have this section about some of the interesting ways people are using Estuary for zero installation live coding workshops, for laptop ensembles, particularly in educational settings. Sometimes people are using Estuary as an instrument in a larger context instead of as the environment for everything that's going on, as well as work deploying Estuary in connection with role-playing, world-building, and gameplay that I think is really fascinating. So I encourage people to check that out in the paper. Okay, so I want to spend a good part now looking at the issue of computational performance in Estuary, because I know from other papers, including Paul's keynote a moment ago, that this is something that this crowd is justifiably very interested in. And I also think it's something that is very important for Estuary. I think that that our project, like so many projects, is unacceptably dependent upon cutting-edge computing hardware And that makes us complicit with all kinds of harmful economies. And I could say more about that, but I imagine that people might know some of the things that I am alluding to. I think that when we optimize things to make them more computationally performant, we're making them work for older computers. And that makes us not so complicit with these cycles of planned obsolescence that are so harmful. So, one of the things I did then, between submitting the camera-ready paper for this talk and getting ready for today's presentation, was to do some crude profiling of how Estuary performs. And I came up with a test called the SAC16 test. And how it works is that we execute the following tidal cycles code while observing measurements of CPU load on a machine. And the code is there, and what it does is it generates a pattern of 16 overlapping sample playback events per cycle, 16 per 2 seconds. And initially, with note 0, the length of each of those sample events is 4.45 seconds. And if you do the math, that leads to approximately 35.6 continuing playback events when things build up into a steady state. If you transpose things downwards, an octave at a time, you double the length of the sample events. So with each octave down, the number of continuing playback events doubles. For example, at note 0, 35.6 steady state playback events. Note minus 24, 142.4 steady state playback events. Note minus 48, 569.6 steady state playback events. And at minus 60, 5 octaves down, approximately 1,140 steady state playback events. And so this test is designed to increase the computational load for audio processing while keeping the load for generating and communicating event parameters constant. So there's always 16 new events per cycle, but those events last longer and generate more need for audio processing as we progress through the test. The system I've used for the figures I'm going to share with you today is the system I'm using right here during this presentation. It's a slightly older gaming desktop that is running Debian 11 and Chrome 103, in other words, up-to-date Debian and Chrome versions. Okay, so here, this slide shows us the quiescent system load. All I've done is launch the operating system, the window managers come up, nothing else is happening. And then this next slide shows the quiescent load with Chrome launched, and still looks basically the same. Here's the quiescent load with Estuary launched, and we see that a bunch of cores are starting to work on things, but still we're kind of at the bottom of the graph. Now, here's the graph when I do a first SAC16 test, the one with note 0, no transposition. And if you pay close attention, one of the cores, this red line at the top, has started to ever so gently leave the rest of the pack. If I go down an octave, that's even more clear. That core is up at about 20% now. Here's at minus 24, and we're just kind of under 30% with some peaks over that. Here we are with 36, by which time we have 285 notes going. We're kind of up about 40%. Qualitatively, things still sound good. Here's at minus 48, and we have 600 continuous events. We're using about 50% of the core, and things still sound good and are almost completely glitch-free. Finally, when we get to minus 60 and 5 octaves down, we have those 1,140 events, and we've definitely maxed out the system. And boy, all those unused CPU cores are starting to look very tasty at this moment. So stepping back from that for a second, let's compare that performance with SuperDirt, which is the sampling engine that exists for tidal cycles that runs in Super Collider. And there's a little tool called the SuperDirt socket that allows Estuary to send sample events to SuperDirt and Super Collider instead. So this is a nice way of kind of comparing what happens when we use a similar, more or less native application to generate the audio. And so on the next series of graphs, the top one is always the WebDirt one, and that runs in the Web Audio API, and the bottom one is SuperDirt and Super Collider. So at note 0, things look pretty similar. As we go down an octave, they still look similar. As we go down another octave, still kind of similar, kind of hovering in the 30% zone. We go down another octave, things are kind of around 40%, more uneven on the super collider side. We go down 4 octaves. The web dirt is where it was before at about 50%. The super dirt super collider one, a second core or a second thread has started to run, and so we're seeing something kind of like 40 plus 20. And anecdotally, we are starting to hear glitches with super dirt super collider. And finally, again, when we go to 5 octaves down, both of them are basically maxed out, but in different ways, and things are glitchy in both cases. As an additional comparison, do the same test again, but this time it's Estuary and WebDirt versus Tidal and SuperDirt being used completely outside of the browser. And so at the first level of the test, that's how things look. Things look a little bit better for the completely native situation. We go down another octave. They look roughly equivalent. We go down another octave. The native application is actually causing more computational load. Go down another octave. That pattern continues, although they're still roughly comparable. And at the next octave down, the native application is quite a bit beyond the web audio API application, and things are already glitchy for the native application. When we go to 5 octaves down, again, everything is maxed out for both situations. So a few conclusions about this test. One, the limit of simultaneous continuous playback events with WebDirt in Estuary seems to be somewhere between 500 and 1,000 events on this okay but slightly outdated machine. And now, while 500 to 1,000 events may seem like a lot, that's a budget that disappears rapidly with longer samples, larger groups, microsound techniques, duplicated transformed layers, less powerful computers, etc. Offloading audio playback to one additional dedicated core wouldn't change this test result much, but it still might help if that main thread was loaded with other things, like parsing live coding languages or generating events. Offloading the playback to something that can access all of the available cores would probably help a lot more. I'm unclear if moving to well-optimized WASM would drastically improve performance on such a relatively simple test, which is just playing back a sample at different playback rates. WebDirt performance, we saw, it currently is roughly similar to SuperDirt Super Collider within the artificial limits of this test, and so a huge thanks to everyone who's been making the web audio API so amazing. So briefly, another area of further work for Estuary is in the area of more modularity. So we're starting to see early signs of what I'm calling exolangs, or exoteric languages, which are live coding languages that are defined externally to the platform as JavaScript modules that provide a predetermined API. And the first prototype of such a language is the language Locomotion. You can search for Locomotion live coding on YouTube to find this video demo of an early version of this language that is focused on dance and choreography and 3D avatars. Works in Estuary in close combination with the various musical languages that are available there. I'm also looking forward to the possibility of exo widgets, which would be widgets in Estuary's view system that would be defined externally. And the purpose of all this work on modularity is so that the Estuary system can be kind of like left running for people to do what they want with it. Oh, I don't want to watch that video. So that's where I'll leave things. Maybe there's a time for a question or two. Thanks, Web Audio Conference 2022, for listening. Thanks to the conference organizers for having us. And I look forward to further discussion now and going forward.
Thank you, David. And yeah, just to mention, I said 14 authors, but it's actually 15 now counting. So.
Yeah.
All right, so are there any questions? We have time for one question or two quick questions. Yeah.
I was just wondering if you could play the video.
I'll back up to the first video at the very beginning. I hope the sound works. good sound? Okay, there's a little bit of a taste, but if you go on YouTube and you look for Cybernetic Orchestra, what's the album called? Anyway, if you just look for Cybernetic Orchestra live coding, you'll find there's a playlist of this whole album, all of which was done with Estuary. So it's a nice demo of kind of what Estuary was doing about a year or a year and a half ago.
Thank you. So well, are there any questions? If a quick one can go in, but otherwise, yeah, are there any other questions? Well, I have a quick one then. So I wonder whether there is any kind of spotlight in terms of the number ensemble members. You've been collaborating with huge amount of members and smaller. So is there any sweet spot?
Yeah, thanks. That's an interesting question. I mean, the cybernetic orchestra here at McMaster is usually around 10 people. And so we're kind of stress testing Estuary in that environment a lot because of that. And I think it's with 10 people, it is possible to manage these computational performance things that I'm talking about with a little bit of care. I think once you start going beyond 10 or so people, you typically start to have to manage things in a different way. Maybe there's even more turn taking, even more sitting out and listening, that kind of thing. But I mean, reflecting on that from another perspective, that's not just a computational performance question. I think that's also a question about how people respond in improvisational environments too. Personally, I would be really interested in trying this out in groups that are scaled much beyond 10. Like, what's it like with 30, 40, 50? What do live coding improvisations look like when they have 50 people participating in them? I think that's a really fascinating question, and I think we probably have to push the computational performance piece a little bit further in be able to kind of get into that question and not be distracted too much by problems with getting things rendered. But yeah, a fascinating question and something I'd love to do more with in the future.
You could try it here in WAC next year, maybe?
Sure.
Cool, yeah, so thank you very much. Let's give another big round of applause to David.
Thank you all.
Yeah, and feel free to post questions on Slack also if you have follow-up questions.